I'm going to sit. Good morning. It's great seeing everybody here this morning. If you're visiting with us, we're glad to see you. This morning, we're diving into the suggestion box. And so, lo and behold, when I go into the suggestion box, I pull out a slip of paper to which says, "Can you talk about evolution?" Set your clocks. All right. Now, I understand the need, but I also want you to understand a couple of things. One, I don't have the time to do it all that in one time because people dedicate this to their lives. They dedicate, evolutionists and creationists. You get PhDs in this. You write books about this. You teach classes on this. And, I just don't have the time. But this is a topic that we could come back to every now and then. Also, something else I want you to understand. I'm not a scientist. All right? Some of the things we're going to talk about this morning, I do understand and I see. Some of it does go over my 6'4" head. So, so just keep that in mind. But when it comes to the subject of evolution, in schools and colleges, they like to throw out the Big Bang, which I do like the Big Bang because I find it funny. In the beginning, there was nothing, and it blew up. It's all right. But I don't want us to be people who are scared of science. Christians do not need to be people who are scared of science. In fact, some of the greatest, earliest scientists were Christians. And the reason is because the more we find out about the world and the universe, more it shows that it was created by God. Science does not cancel out God. It adds to it. In fact, a few Wednesday nights ago, we were talking about God and creation. And there's PhDs in over 100 different types of science, ranging from paleontology to archaeology to microbiology to physicists, astrophysicists, and everything, including dentists. They were represented in that list. That believed that there had to have been a creator. Not that there was a creator, that they had faith that there was a creator. That there had to have been a creator. One theory that has come out and was proposed originally, at least as far as I could tell, by a doctor named Dr. Hugh Ross. And he brought out a theory called the fine-tuner theory. And if you don't know what that is, that's fine. But what this says is the proposition that the conditions that allow life in the universe can only occur when certain universal dimensions, physical constants, lie within a very narrow range. So that if any of several fundamental constants were only slightly different, the universe would be unlikely to be conducive to the establishment of development of matter, astronomical structures, elemental diversities, or life as it is understood. In other words, Earth, our solar system, and our Milky Way galaxy, and everything else in between is designed so perfectly. This isn't coming from the Bible. This is what scientists are starting to figure out. It's designed so perfectly, the chances of it just happening, order out of chaos, becomes more and more unlikely. This is what knowledge is starting to show us. To which those of us who believe in the Bible, we say, well, yeah. But what does a planet need for life? This is what the big question is. What does a planet need for life? In 1966, there was a scientist named Carl Sagan. And he said that there are two parameters that are needed for a planet to support life. The right kind of star, our sun, and the planet the right distance from the star, so as to not to be too hot or too cold. And if you have this, you have a planet that can support life. But again, this was 1966. As time moved forward, scientists have discovered more and more factors that are needed for a planet to support life. This morning, I want to take you through some of these. Not deeply, because again, I'm not a scientist. But what I wanted to show you is knowledge. Now, again, this is coming from scientists. In other words, they might use language in what I'm proposing that might coincide with some sort of stepchild Big Bang theory. I'm not saying that I believe it. What I'm saying is this is what they are starting to find. And what they're starting to find is more and more evidence that these things cannot just happen. The risk is too big, because what we go through, if any one of these was just a little bit off, and this, keep this in mind, this is something that we can all get. If any one of these was just a little bit off, life would not work on this planet like it does now. Okay? So that's what we're going to do this morning. And in fact, I scared Buddy because I got a bunch of slides, and I told Buddy, don't worry about it. If this thing doesn't work, I'll go to the back and run it from the back. So here we go. What does a planet need to support life? Presenting God, the fine-tuners. Strap on your seatbelts. Here we go. All right, galaxy cluster type. If too rich, galaxy collisions and mergers would disrupt solar orbit. If too sparse, insufficient infusions of gases to sustain star formation for a long enough time. Galaxy size. If too large, infusion of gas and stars would disturb Sun's orbit and ignite too many galactic eruptions. If too small, insufficient infusions of gas to sustain star formation for long enough time. Galaxy type. If too elliptical, star formation would cease before sufficient heavy element buildup for life chemistry. If too irregular, radiation exposure on occasion would be too severe and heavy elements for life chemistry would not be available. Galaxy mass distribution. If too much in the central bulge, life-supportable planet would be exposed to too much radiation. If too much in the spiral arms, life-supportable planet would be destabilized by the gravity and radiation from adjacent spiral arms. Galaxy location. You are here. Just in case you know. If too close to a rich galaxy cluster, galaxy would be gravitationally disrupted. If too close to a very large galaxy or galaxies, galaxy would be gravitationally disrupted. If too far away from dwarf galaxies, insufficient infall of gas and dust to sustain ongoing star formation. Hypernova eruptions. If too few, not enough heavy element ashes present for the formation of rocky planets. If too many, relative abundance of heavy elements on rock planets would be inappropriate for life. Too many collision events on planetary system. If too soon, leads to a galaxy evolution history that would disturb the possibility of advanced life. Not enough heavy element ashes present for the formation of rocky planets. If too late, leads to a galaxy evolution history that would disturb the possibility of advanced life. Relative abundances of heavy elements on rocky planets would be inappropriate for life. Too many collision events in planetary system. Got to turn my page. Supernova eruptions. If too close, life on planet would be exterminated by radiation. If too far, not enough heavy element ashes would exist for the formation of rocky planets. If too infrequent, not enough heavy element ashes present for the formation of rocky planets. If too frequent, life on the planet would be exterminated. If too soon, heavy element ashes would be too dispersed for the formation of rocky planets at an early enough time in cosmic history. If too late, life on the planet would be exterminated by radiation. White dwarf binaries. If too few, insufficient fluorine would be produced for a life chemistry to proceed. If too many, planetary orbits disrupted by stellar density life on a planet would be exterminated. If too soon, not enough heavy elements would be made for efficient fluorine production. If too late, fluorine would be made too late for incorporation in protoplanet. Proximity of solar nebula to a supernova eruption. If farther, insufficient heavy elements for life would be absorbed. If closer, nebula would be blown apart. Timing of solar nebula formative relative to supernova eruption. If earlier, nebula would be blown apart. If later, nebula would not absorb enough heavy elements. Number of stars and parent star birth aggregate. In other words, number of suns. If too few, insufficient input of certain heavy elements into the solar nebula. If too many, planetary orbits would be too radically disturbed. Star formation history and parent star vicinity. If too much too soon, planetary orbits will be too radically disturbed. Planet-star distance from the closest spiral arm. If too large, exposure to harmful radiation from galactic core would be too great. Z-axis. Heights of star's orbit. If more than one, tidal interactions would disrupt planetary orbit of life support planet. If less than one, heat produced would be insufficient for life. Number of stars in the planetary system. If more than one, tidal interactions would disrupt planetary orbit of life support planet. If less than one, heat produced would be insufficient for life. Parent star age. If older or younger, luminosity of star would change too quickly. Parent star mass. If greater, luminosity of star would change too quickly, star would burn too rapidly. If less, range of planet distances for life would be too narrow. Tidal forces would disrupt the life of planet's rotational period. UV radiation would be inadequate for plants to make sugars and oxygen. Parent star metallicity. If too small, insufficient heavy elements for life chemistry would exist. If too large, radioactivity would be too intense for life. Life would be poisoned by heavy element concentration. Parent star color. If redder or bluer, photosynthetic response would be insufficient. Galactic tides. If too weak, too low of a comet ejection rate from giant planet region. If too strong, too high of a comet ejection rate from giant planet region. H3 production. If too small, simple molecules essential to planet formation and life chemistry will not form. If too large, planets will form at wrong time and place for life. Flux of cosmic ray protons. If too small, inadequate cloud formation in planet's troposphere. If too large, too much cloud formation in planet's troposphere. Solar wind. If too weak, too many cosmic ray protons reach planet's troposphere, causing too much of cloud formation. If too strong, too few cosmic ray protons reach planet's troposphere, causing too little cloud formation. Parent star luminosity relative to speciation. If increases too soon, runaway greenhouse effect would develop. If increases too late, runaway glaciation would develop. Surface gravity or escape velocity. If stronger, planet's atmosphere would retain too much ammonia and methane. If weaker, planet's atmosphere would lose too much water. Distance from parent star. If farther, planet would be too cool for a stable water cycle. If closer, planet would be too warm for stable water cycle. Inclination of orbit. If too great, temperature differences on the planet would be too extreme. Eccentricity. If too great, seasonal temperature differences would be too extreme. Axial tilt. If greater or less, surface temperatures differences would be too great. Rate of change of axial tilt. If greater, climatic changes would be too extreme. Surface temperature differences would become too extreme. Rotation period. If longer, diurnal temperature differences would be too great. If shorter, atmospheric wind velocities would be too great. Rate of change in rotation period. If longer or shorter, surface temperature range necessary for life would not be sustained. Planet age. If too young, planet would rotate too rapidly. If too old, planet would rotate too slowly. Magnetic field. If stronger, electromagnetic storms would be too severe. Too few cosmic ray protons would reach planet's troposphere, which would inhabit adequate cloud formation. If weaker, ozone shield would be inadequately protected from hard stellar and solar radiation. Oh, look at that, got off. There we go. Thickness of crust. If thicker, too much oxygen would be transferred from the atmosphere to the crust. If thinner, volcanic and tectonic activity would be too great. Asteroid and cometary collision rate. If greater, too many species would become extinct. If less, crust would be depleted of materials essential for life. Mass of body colliding with primordial Earth. If smaller, Earth's atmosphere would be too thick, Moon would be too small. If greater, Earth's orbit and form would be too greatly disturbed. Timing of body colliding with primordial Earth. If earlier, Earth's atmosphere would be too thick, Moon would be too small. If later, Sun would be too luminous at epoch for advanced life. Oxygen to nitrogen ratio in atmosphere. If larger, advanced life functions would proceed too quickly. If smaller, advanced life functions would proceed too slowly. Carbon dioxide level in atmosphere. If greater, runaway greenhouse effect would develop. If less, plants would be unable to maintain efficient photosynthesis. Water vapor level in atmosphere. If greater, runaway greenhouse effect would develop. If less, rainfall would be too meager for advanced life on the land. Atmosphere electric discharge rate. If greater, too much fire destruction would occur. If less, too little nitrogen would be fixed in the atmosphere. Ozone level in atmosphere. If greater, surface temperature would be too low. If less, surface temperatures would be too high. There would be too much UV radiation at the surface. Oxygen quantity in atmosphere. If greater, plants and hydrocarbons would burn up too easily. If less, advanced animals would have too little to breathe. Rate of interior heat loss. If too low, inadequate energy to drive the required levels of plate tectonic and volcanic activity. If too high, plate tectonic and volcanic activity shuts down too quickly. Seismic activity. If greater, too many life forms would be destroyed. If less, nutrients and ocean floors from river runoff would not be recycled to continents through tectonics. Not enough carbon dioxide would be released from carbonates. Volcanic activity. If lower, insufficient amounts of carbon dioxide and water vapor would be returned to the atmosphere. Soil mineralization would become too degraded for life. If higher, advanced life at least would be destroyed. Rate of decline in tectonic activity. If slower or faster, advanced life can never survive on the planet. Rate of decline in volcanic activity. If slower or faster, advanced life can never survive on the planet. Timing of birth of continent formation. If too early or late, silicate carbonate cycle would be destabilized. Oceans to continent ratio. If greater or smaller, diversity and complexity of life forms would be limited. Rate of change in oceans to continent ratio. If smaller, advanced life will lack the needed landmass area. If greater, advanced life would be destroyed by the radical changes. Soil mineralization. If too nutrient poor or rich, diversity and complexity of life forms would be limited. Jupiter distance. If greater, too many asteroids and comet collisions would occur on Earth. If less, Earth's orbit would become unstable. Jupiter's mass. If greater, Earth's orbit would become unstable. If less, too many asteroid and comet collisions would occur on Earth. Drift in major planet distances. If greater, Earth's orbit would become unstable. If less, too many asteroid and comet collisions would occur on Earth. Major planet eccentricities. If greater, orbit of life-supportable planet would be pulled out of life support zone. Major planet orbital instabilities. If greater, orbit of life-supportable planet would be pulled out of support zone. Mass of Neptune. If too small, not enough Kuiper belt objects, asteroids beyond Neptune, would be scattered out of the solar system. If too large, chaotic resonances among the gas giant planets would occur. Kuiper belt asteroids beyond Neptune. If not massive enough, Neptune's orbit remains too eccentric, which destabilizes the orbit of other solar system planets. If too massive, too many chaotic resonances and collisions would occur in the solar system. Atmospheric transparency. If smaller, insufficient range of wavelength of solar radiation reaches planetary surface. If greater, too broad a range of wavelengths of solar radiation reaches planetary surface. Magnitude of duration of sunspot cycle. If smaller or shorter, insufficient variation in climate and weather. If greater or longer, variation in climate and weather would be too much. Continent relief. If smaller, insufficient variation in climate and weather. If greater, variation in climate and weather would be too much. Chlorine quantity in atmosphere. If smaller, erosion rates, acidity of rivers, lakes, and soils, and certain metabolic rates would be insufficient for most life forms. If greater, erosion rates, acidity of rivers, lakes, and soils, and certain metabolic rates would be too high for most life forms. Iron quantity in oceans and soils. If smaller, quantity and diversity of life would be too limited for support of advanced life. If very small, no life would be possible. If larger, iron poisoning of at least advanced life would be result. Tropospheric ozone quantity. If smaller, insufficient cleansing of biochemical smog would result. If larger, respiratory failure of advanced animals, reduced crop yields, and destruction of ozone-sensitive species would result. Stratospheric ozone quantity. If smaller, too much UV radiation reaches planet's surface, causing skin cancers and reduced plant growth. If larger, too little UV radiation reaches planet's surface, causing reduced plant growth and insufficient vitamin production for animals. Mesospheric ozone quantity. If smaller or greater, circulation and chemistry of mesospheric gases so disturbed as to upset relative abundances of life-essential gases in lower atmosphere. Quantity of soil sulfur. If smaller, plants will become deficient in certain proteins and die. If larger, plants will die from sulfur toxins. Acidity of water and soil will become too great for life. Nitrogen cycle will be disturbed. Biomass to comet infill ratio. If smaller, greenhouse gases accumulate, triggering runaway surface temperature increases. If larger, greenhouse gases decline, triggering runaway freezing. Total mass of Kuiper belt asteroids. If smaller, Neptune's orbit will not be adequately circularized. If larger, too severe gravitational instabilities generated in outer solar system. Solar magnetic activity level. If greater solar luminosity, fluctuations will be too large. Density of brown dwarfs. If too low, too many low-mass stars are produced, which will disrupt planetary orbits. If too high, disruption of planetary orbits. Distances from nearest black hole. If too close, radiation will prove deadly for life. Absorption rate of planets by parent star. If too low, disturbs sun's luminosity and stability of sun's long-term luminosity. If too high, disturbs orbits of inner solar system planets, disturbs sun luminosity and stability of sun's long-term luminosity. Star rotation rate. If too slow, too weak of a magnetic field resulting in not enough protection from cosmic rays for life support planet. If too fast, too much chromospheric emissions causing radiation problems for the life support planet. Rate of nearby gamma ray bursts. If too low, insufficient mass extinctions of life to create new habitats for more advanced species. If too high, too many mass extinctions of life for the maintenance of long-lived species. Density of interstellar and interplanetary dust particles in vicinity of life support planet. If too low, inadequate delivery of life essential materials. If too high, disturbs climate too radically on life support planet. Thickness of mid-mantle boundary. If too thin, mantle convection eddies become too strong, tectonic activity and silicate production become too great. If too thick, mantle converting convection eddies become too weak, tectonic activity and silicate production become too small. Gamma ray burst events. If too few, not enough production of copper, scandium, titanium, and zinc. If too many mass extinction events. Cosmic ray luminosity of Milky Way galaxy. If too low, not enough production of boron. If too high, lifespans for advanced life too short, too much destruction of planet's ozone layer. Air turbulence in troposphere. If too low, inadequate formation of water droplets. If too great, rainfall distribution will be too uneven. Primordial cosmic superwinds. If too low of an intensity, inadequate star formation late in cosmic history. If too great of an intensity, inadequate star formation early in cosmic history. Smoking quasars. If too few, inadequate primordial dust production for stimulating future star formation. If too many, early star formation will be too vigorous, resulting in too few stars and planets being able to form late in cosmic history. Mantle plume production. If too low, inadequate volcanic and island production rate. If too great, too much destruction and atmospheric disturbances from volcanic eruptions. Quantity of proto-neutron stars with very strong magnetic fields. If too few during galaxy's history, inadequate quantities of our process elements are synthesized. If too many during galaxy's history, too great a quantity of our process elements are synthesized, too great of a high energy cosmic ray production. Frequency of gamma ray burst in galaxy. If too low, inadequate production of copper, titanium, and zinc, insufficient hemisphere-wide mass extinction events. If too great, too much production of copper and zinc, too many hemisphere-wide mass extinction events. Parent star magnetic field. If too low, solar wind and solar magnetosphere will not be adequate to thwart a significant number of cosmic rays. If too great, too high of an X-ray flux will be generated. Parent star distance from galaxy's co-rotation cycle. If too close, a strong mean motion resonance will destabilize the parent star galactic orbit. If too far, a planetary system will experience too many crossings of the spiral arms. Frequency of late impacts by large asteroids and comets. If too low, too few mass extinction events and adequate rich ore deposits of furious and heavy metals. If too many mass extinction events, too radical disturbances of planet's crust. Size of the carbon sink and the deep mantle of the planet. If too small, carbon dioxide level in planet's atmosphere will be too high. If too large, carbon dioxide level in planet's atmosphere will be too low. Biomass will be too small. Rate of growth of central spheroid for the galaxy. If too small, inadequate flow of heavy elements into the spiral disk, inadequate outward drift of the stars from the inner to the central portions of the spiral disk. If too large, inadequate spiral disk of late-born stars. Amount of gas infalling into the central core of the galaxy. If too little, galaxy's nuclear bulge becomes too large. If too much, galaxy's nuclear bulge fails to become large enough. Level of cooling of gas infalling into the central core of the galaxy. If too low, galaxy's nuclear bulge becomes too large. If too high, galaxy's nuclear bulge fails to become large enough. 95. Quantity of volatiles on and in Earth-sized planet in the habitable zone. If too low, inadequate ingredients for the support of life. If too high, no possibility for a means to compensate for luminosity changes in stars. Triggering of El Nino events by explosive volcanic eruptions. If too seldom, uneven rainfall distribution over continental land masses. If too frequent, uneven rainfall distribution over continental land masses. Too much destruction by the volcanic events, drops in mean global surface temperature. All right, I expect Rebecca Dunn expects your research papers turned into the office next Monday. No. Yes, there's going to be a test. Now, I shared with you 96 because my computer can't count. I had a little technical glitch. But I want you to know something. If you thought that was very wordy, you should try reading it. All right? But there are still more than 100 parameters needed for life to exist. The total number, are they up to? I don't know the total number. What I do know is that it is 200 plus parameters that scientists are saying that are needed in order for life to exist on the planet. It started at 2, they're up to 200 plus. Now, hopefully, I know I went through that fast because I knew you didn't want to be here all day. We already lost an hour of sleep. I didn't want to tempt anybody. But with each parameter means more control, more organization. When is the point in which we look and say, there is no way this could have happened by chance? It's too perfect. If you notice the list that I shared with you, now again, I shared with you the short ones, okay? And also the ones with words that I could pronounce. But in that list, we talked about the planet. We talked about the mantle. We talked about the soil. We talked about the atmosphere. We talked about the sun. We talked about Neptune, for Pete's sake. When was the last time you thought about Neptune? We talked about Jupiter. We talked about the solar system as a whole. And we talked about the Milky Way galaxy. If something was off in any of those levels, we would not be here. We would not be here. Now again, theorists say, the Big Bang Theory says that the foundations of our existence were laid 1 nanosecond, which is 1/billionth of a second after the Big Bang occurred. Now, we try to wrap our heads around what a nanosecond is, and I actually found this. It says 1 nanosecond is to 1 second as 1 second is to 31.71 years. In fact, I saw another measure that said you've actually lived 1 billion seconds by the time that you hit the age of 31. Now, what this shows us is, according to some, there was a whole lot of perfect, precise chaos, order coming out of chaos that happened very rapidly. And they make fun of us for having a belief in God. But again, some people are starting to come around. Peter Schinkel, who's an atheist, retired political scientist, author with an interest in extraterrestrial life, said this: in light of new findings and insights, we should quietly admit, I love the quietly part, we should quietly admit that the early estimates may no longer be tenable. In other words, what he's saying is, the more we learn, the more we got to realize that the way we think the Big Bang happened is not the way it happened. Order out of chaos. And this throws in evolution, and this throws in all those types of theories. Because again, knowledge is power. And the more we learn about our planet, the more we learn about the universe, the more we learn about what is needed versus what is not needed for life, and how, again, some call it the Goldilocks cycle. You know, it can't be too hot, it can't be too cold, it has to be just right. The more they figure out how this stuff has to be just right, so much has to be just right in order for life to exist, well, that points to a higher power who had to put it together. Now, but this is the thing about looking at science. And again, we shouldn't be Christians who are scared of science. We have nothing to fear about science. We really don't. Because the more that is learned, the more that, again, the more it points to a creator. But that doesn't take out faith. The Hebrew writer will go on to say that without faith, it is impossible. Think about the phrasing he's using. He's not saying without faith it is very difficult. Like without faith we need to try a little. No, without faith it is impossible to please God. We can show somebody all the evidence in the world, or we can be shown all the evidence in the world. But for us or for other people, there comes a time, there comes a point where we have to say, okay, who do I believe created it all? There's been many higher powers that have come down the history of the world. Many. That are not God. But we have faith. Who created the heavens and the earth? We know God did. Not some other higher power. God did. We know that God laid the foundations for the heavens and the earth. He laid the foundations for the galaxies. He laid the foundations for all the systems that work so perfectly in this world of ours. And He created it. And He said, it is good. God didn't give us His off day stuff. He created for us a perfectly working, perfectly functioning place to live. And He says, it is good. Is it possible for life to have just happened? No. We can go with the Han Solo thinking. The more we learn about how much various elements are needed to sustain life, we can be like Han Solo and say, you know what, don't tell me the odds. Because the odds get way more and more and more and more gigantic the more that's needed. No. We're able to have faith. God made this place. And science proves it. This morning we like to offer the invitation to anyone who has a need. Because it is tempting. It's easy in this world to be tempted with the way the world's going, with looking out and saying, well, if God's in control, where is He? And things similar to these thoughts. God's here. And He's still watching. He's still creating. He created this world out of love. Because that's another interesting question. We talked about that a few Wednesday nights ago. If God can do anything, why did He choose to create? Who said He had to create a world? Who said He had to create us? The answer is He didn't. But He chose to. He chose to because He wanted us to be with Him. And this is what God has always wanted. He has always wanted us to be with Him. This morning, if you're with us this morning and you have not given yourselves over to baptism, to have your sins washed away, so that we may have the hope of being with God one day, we would love to assist you with that this morning. But whatever needs you have, would you please come down as we stand and as we sing.